So now let's take a little bit of a detour and talk about signals as vector spaces, or signal spaces as vector spaces. This is a more abstract way of looking at signals and introduces this important notions of geometry into our story about signals and systems. So basically we want to be able to interpret signals as vectors. So what's a vector space? Now, linear algebra is not a prerequisite for this class, so this might be new to some of you. But a vector space, and you can think of just d-dimensional vectors or two-dimensional vectors if you like, real vectors. A vector space is a set of objects, which are called vectors, and there are two operations you can do with these. You can do scalar multiplication, so these are vectors defined over some field, which is like the real numbers or the complex numbers, so those are scalars. So you can multiply a vector by a scalar, and you can also add two vectors together. That's vector addition. And basically, addition and scalar multiplication behave like you want them to behave. They're associative and commutative and distributive, and there's also a zero vector such that, if you add 0 to x, you get back x, and there's a minus x for every x, so if x is a vector, there's a minus x, which is gives you 0. And basically, and there's an identity element 1, a scalar 1, such that 1 times x is equal to x. So these are the properties that a vector space has to satisfy, and this is sort of the formal definition of a vector space. So in what way are signals a vector space? That's the question we want to answer for ourselves. Now, we saw in the way that we had dealt with things computationally that discrete time signals are just vectors in MATLAB, so they're kind of already vectors. But real signals, may be infinite in length, so how do we deal with that? So how do we define a notion of what a vector is there? So we've already seen vector spaces like n-dimensional real space, or maybe n-dimensional complex space if you have a complex signal of length n. And so why are we making such a big deal out of talking about signals as vectors? Because these signals, we think of them as vector spaces, as vectors in a vector space of functions, or a function space. And the reason to do this is because it lets us think about these signals. When we think about them as vectors, then we think about vector properties like angles between vectors or the length of vectors. And these turn out to be related to quantities that we care about when we do signal processing and the basic stuff for signals and systems. So since we're going to focus mostly on linear systems, that means it's a linear function of the signal, which means that a linear function of the signal is just a matrix. So if I take a linear function of a vector, it's just multiplication by a matrix. So you can think of systems as being essentially acting like matrix multiplication. And suddenly, all of the operations that we're looking at turn into basically algebra operations, linear algebra operations. Another concept that's important when we talk about vector spaces, when we talk about vectors, is a basis. So we want to be able to write vectors in terms of simpler vectors, like we can write vectors in terms of linear combination of coordinate vectors. And so that's just a basis for the vector space. And so it turns out that when we do Fourier transforms, it's like doing a change of basis for our vector space. That is, when we take this Fourier transform, what we're going to be doing is basically looking at the signals according to a slightly different geometry by choosing different basis vectors. So we need to think about what is the space of functions or signals that we're thinking about. And this is called a function space, or a vector space of functions. So what we're going to consider are bounded energy functions. So this continuous time signals, L2 of R, is basically all signals with finite energy. And similarly, L2 of Z, which is all signals, discrete time signals with finite energy. And this R and this Z represent the time axis in this case. So these functions could in general be complex valued. These signals can be complex valued. So if you think about the signals in these two sets, bounded energy functions, bounded energy signals in both the continuous time and discrete time, if you go through the axioms that I mentioned before, those 8 axioms, with scalar multiplication just being multiplication by a complex number and vector addition just being addition of functions, you should be able to check that all of those conditions are satisfied. And you might feel like it's a little weird just verifying like equation, then you write it down and you'll say, oh, of course that's true. But you should check. It's important to sort of just go through the formal process of checking it. It helps. Product. So now that we've defined what function space we're looking at, these bounded energy functions, we can talk about geometric properties, such as the inner product. So what is an inner product? It's just the dot product. Inner product is maybe a fancier name for dot product. When we define the inner product between functions, we define it as an integral of the product of the functions. So let's look at the discrete time version first. So here we can see we're basically taking x dot y star. So we're taking x dot y conjugate, and then we're adding it up. So if x and y were just finite length vectors, then you would just be taking the regular dot product, except for there's this star here. And that's because we're dealing with complex functions. And so with this definition of inner product, we have actually that the dot product is not symmetric. That is, it's not x dot y is not y dot x, but x dot y is y dot x star. So in continuous time, you do the same thing, but if you did this in MATLAB, you would just be doing it for these discretized versions of the continuous signal. But we just multiply x of t times y star of t and integrate that. So that's what we mean by the inner product in these function spaces. So in real space, that is, if we look at real finite dimensional vectors, we have x inner product with y is just x transpose y, if you think about it in terms of matrices, which just means that x dot x, which is x squared, norm of x squared. It's the squared length of x, right? So here we can see the connection between the geometry. So the magnitude of a vector is the square root of the energy of the vector, right? So the squared norm of a signal is the same thing. We take x of t inner product with x of t itself, and then we get x of t times x star of t. That gives us magnitude of x of t squared, and this is just then defined by the energy. And similarly in discrete time, this is just x inner product with x, and then we get x of absolute magnitude of x of n squared, and then we get the energy at Ex. Right, so the energy of a signal is just the squared length of that signal when we think of it as a vector. So this actually ties energy to a geometric notion of length, or squared length. What about projections? So we think of x transpose y, or x dot y, as the component of x in the direction of y, or the projection of x onto y. And the same thing is true for functions in signal spaces with an inner product. So if you want to talk about how much is this signal like this other signal, you can take this inner product between the two signals, and that'll give you some kind of coefficient. And remember, you can define the cosine of an angle between two vectors in terms of this inner product between the two vectors. So similarly, you can define a cosine theta kind of relationship between different signals. So we can talk about whether signals are correlated or not correlated based on this. And this autocorrelation function that we saw before is exactly doing this kind of thing. If you write out the formula and take a look, you'll see this is kind of a way to understand the autocorrelation function. So we'll see later, of course, that the Fourier transform is just an inner product of x with a complex exponential. So we're actually just projecting the signal x onto a new basis, this complex exponential basis. There's a little bit of a caveat here, of course. These two complex exponentials are power type signals, so they don't have finite energy. So there's a little bit of hand waving that I'm doing here. So what about linear systems or linear transformations? So if you think about linear algebra, we often talk about matrices times vectors. I mean, that's just that's the thing. You have a vector, and one thing you can do with it is multiply it by a matrix. So can we do the same kind of interpretation for signals? And it turns out, yes, we can think of linear systems as being multiplication by like an infinitely large matrix. So it's a little hard to think about, but think about growing this finite length matrix and this finite length vector. So this vector here, and we start growing it up and down. And if we grow it up and down, we have to grow the matrix up and out, and up and out. So we have to expand the matrix as we expand the vector, and you can see we're going to you can sort of picture how it's going to look in terms of generalizing this matrix multiplication. This is not actually a good way to do it computationally, but it's sometimes a useful way of thinking about it, especially when you're thinking about very long signals and what's happening with very long signals. For CT signals, this kind of analogy is like much more abstract, and so maybe it's not as useful to think about continuous time signals in this way. So suppose I wanted to have a system which is just the identity system. That is, it returns the vector itself. So I have g times x, and I should just get back x, right? And this is for all x. Right, so this is just, you can think of it as scalar multiplication by 1, but as a matrix, it would be G is the identity matrix, which in MATLAB is, I of n would give you an n-dimensional identity matrix. So what about a delay by 1? If I wanted to take a vector and I wanted to shift all the elements down by 1, I would just shift the diagonal of that identity matrix, which remember looks like this, 1, 1, hold on, diagonal 1. So I'm going to shift this, so if I want delay 1, I'm going to shift it so that it's 0, 1, 0, 0, 0 on the diagonal, and then 1, 1, 1, dot, 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 and then 0 over here and 0 over here. And what is that doing? That's shifting matrix multiplication is going to shift the first coordinate to the next coordinate down. And this is how you can do a delay by matrix multiplication. And when you think about this infinite matrix, the system is going to look exactly like this. So, just to sum up, a lot of this was a little bit abstract, but it's just trying to give you a flavor of what is actually going on maybe under the hood of some of the things we're talking about in terms of the linear algebra and geometry of the signal analysis. So useful things to remember out of here are that inner products are just projections, energy is the squared length of the signal as a vector, and linear transformations can look like matrix multiplication, especially for discrete time. So try computing the inner product between signals like cosine omega t and sine omega t, and try it with complex signals. Try computing some of these inner products, and that will give you some practice in trying to understand maybe a little bit what's going on, and at least gives you some more facility and familiarity with doing these kind of operations.